you guys see my screen? It's weird. Ah, here we go. All right, class 5. Let's talk about our course in general. I plan for 8 classes. So class 5, you guys can all do math. We're more than halfway through our course. I don't know about maybe a class 9. I'm thinking like I want you guys to do an AMC or probably, yeah, just an AMC. And I can review with each of you individually what mistakes you made or what problems you want to go over. But I don't think that'll be an entire class. So 8 full classes, and this is the 5th one. So after today, we have 3 more. All right, we're not going over homework today because I think pretty much everyone got all of them right. But if you haven't turned in your homework and you're having trouble on a problem, feel free to shoot me an email. I'll be available. No, I won't, actually. Tomorrow's the first day of school, so probably every evening I'll be available, but definitely not in the mornings anymore. All right, so we're finishing up triangles. We're going to talk about triangle similarity and then different parts of triangles like altitudes, medians, Pythagorean theorem. And then we'll move on to quadrilaterals and specific types of quadrilaterals like cyclic quadrilaterals, which we'll learn about very last. All right, similar. So I'm sure many of you already know this. Similarity is just having 2 or more figures. Sorry, 2 or more figures are similar if one or the other can be scaled down or up to the other. So basically, I can multiply all the sides by some number, some ratio, let's call it R, and then that'll create the other triangle. That'll create the sides of the other triangles or the other figure. So we talked about congruence last class, and this class we're going over similarity, which is also going to show up in math competitions. Okay, their side lengths are proportional. So in this case, C divided by F, so let's turn on annotations. This side length C and this side length F are proportional to each other. We've learned what proportional means in another class. Same goes for B and E and A and D. So it's important to note in figures which sides are actually similar to the other, because B and D aren't similar. It's B and E. I think there's, oh yeah, see, and all of these proportions are equal to each other because you're multiplying by the same ratio or scale. I don't think I really need to go over more. All right, AA similarity. All right, so A stands for angle. If 2 angles of a triangle equal 2 of another triangle, then the triangles are similar. I mean, this makes sense, right? Because, let's go back to the other slide. If you have, by definition, every triangle can be defined by what their angle lengths are and what their side lengths are, and all you're doing in similarity is just changing how long the side lengths are, so the angles won't change at all. So we call it AA similarity instead of AAA because, well, all angles add up to 180, so we don't really need 3 angles to prove it. We just need 2 that are the same to prove similarity. All right, here's a question. Why does AA not imply congruence? What is 2A? Actually, did I turn on chat?
Because a bigger triangle can still have the same angles.
Yeah, because as I just talked about, side lengths are going to be changed by similarity, and we just proved that AA creates similarity but not congruence. Similarity, which means that the sides don't have to stay the same. Okay. Earbuds need to go off. All right, we have other similarities. Actually, you probably won't use these that much at all, but it's good to know. Side angle side. So basically in this case, when two sides are proportional to the other and the angle between those two sides are equal, that creates similarity as well. But you definitely, I'd say like, no, I'm gonna say I'll call it now. You'll never use side angle side. I don't even know why I included it, but it's good to know. Side 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 is just by definition. If three sides of a triangle have the same ratio as another triangle, they are similar. All right, solve it. X and Y are on sides PQ and PR respectively of triangle PQR. I'm gonna draw this while you guys write it out. Such that XY is parallel to QR. That's what that that's what those two vertical lines mean, by the way, parallel. Given XY equals 5, QR equals 15, and YR equals 8, find PY. Huh. Okay, so X and Y are on sides PQ and PR respectively, such that XY is parallel to QR. X, Y. All right, and we use these arrows to say that these two lines are parallel. We know that XY is equal to 5 and QR is equal to 15. And YR is equal to 8. Okay, cool. What does the question ask for? They're asking for this side. PY. All right. Does anyone have any ideas?
Me.
Oh yeah, go ahead, Maxwell.
16.
16, huh? Can you explain?
Four. Yeah.
That answer.
Yes, 4. So because
It's okay if you can't really articulate it.
so basically PXY is similar to PQR.
Yeah. Okay. Why do you think that? You can't just say that it is similar because it looks like it.
Because angles Y and angles Y and R are equal, and angles X and Q are equal.
How do you know that they're equal?
Because X, Y, and QR are parallel.
Yeah, exactly. And let's talk about that. Last class we talked about corresponding angles. And that means that when you have two parallel lines and a transversal such as PR goes through those two parallel lines, they create corresponding angles that are congruent to each other. So in this case, it would be angle R and angle PYX. Oh yeah, Maxwell, next time, don't forget that you have to label this angle PYX because angle Y could mean PYX or RYX. Same goes for angle X. All right. And then on the other side, there's also another transversal. So we have these two angles. All right, this creates AA similarity, angle-angle similarity. We have two triangles, PYX and PRQ, that are similar to each other. Now, by definition of similarity, we know that these two triangles have the side lengths of these two triangles are proportional. So therefore, they have the same ratio between them. In this case, they already gave us what two sides are. In this case, 5 and 15. So we know that triangle PYX is a third is triangle PRQ scaled down by a third. What does this mean? Well, we know that since 5 yx, by the way, yx times 3 is going to be equal to 15 for RQ. We can do the same logic for PY and PR. Okay, so PY was, we called that X. Actually, I probably shouldn't have called that X since we already have an X, but oh well. So X times 3 is going to be equal to X plus 8. That's what PR is. All right, this is just simple algebra with, let's subtract X from both sides. We get 2X is equal to 8, and we find that X is equal to 4, as Maxwell stated earlier. Does anyone have any questions about how we got this answer? Yep. All right. Oh, here's a solution. All right. Triangle inequalities. I don't know why I put this here. Should have put it later on. Okay, so the triangle inequality theorem. So this is a theorem that's definitely going to show up in math counts and AMC. Basically, it states that the sum of the lengths of any two sides of a triangle is greater than the sides of the third side. Any two sides. What this means in this case is A plus B has to be greater than C, A plus C has to be greater than B, and B plus C has to be greater than A. Okay. A plus B is greater than C. Okay. But all you need to do in this case is, in most cases, is prove that the smallest two sides, when added together, are still greater than this third side. Did I give a problem for this? No, I didn't. Let me come up with an example right now. They could give you like two sides of a triangle, 3 and 7 or something, and ask to find how many other integers can be the third side of the triangle. Let's solve that really quickly. 3 and 7. All right. So we know that 3 plus 7 has to be greater than this third side. Let's call it C. 3 plus C has to be greater than 7. And 7 plus C has to be greater, wait, what? Yeah, greater than 3. All right, because we know that C is positive, this one doesn't really matter. All right, 3 plus C is greater than 4, so C has to be greater than, 3 plus C is greater than 7, so C is greater than 4. On the other hand, C also has to be less than 10 by the first equation. So we have 5, 6, 7, 8, 9. That is 5 values for C. This also applies for all other polygons. So if I were to give you a quadrilateral, 3 sides have to add up to more than the fourth side. And so on. All right, Pythagorean theorem. Okay, how many of you guys already know about the Pythagorean theorem? Just curious.
Me.
Maxwell, cool. Feel free to chat if you don't have your mic. Okay, Barika. Oh, hopefully I'm pronouncing that correctly. Barika. That's strange. Okay. Okay, let's move on then. Named after mathematician. Okay, so you can tell it's made by some guy. It's named after some guy, Pythagoras. He didn't make it. So there's 367 different proofs. Okay, so Pythagorean theorem is a special formula for right triangles. Remember last class we talked about how right triangles, the biggest side is going to be the hypotenuse, and that's going to be opposite this right angle. Then the other two sides are going to be called the legs. All right. And what this theorem states is a squared plus b squared plus c squared. Okay. Let's talk about this. There's many ways to prove this. I guess the easiest way would be to form a square with a squared and b squared, because that's the area of the square. And then for c squared, form 3 squares, and you'd find that the areas of AB and the areas of the squares formed by A and B would add up to the area formed by C. All right, most common Pythagorean triple. Okay, so Pythagorean triples are just numbers that can be the side lengths of a right triangle. So in this case, 3, 4, 5, you note that 3 squared plus 4 squared is going to be 9 plus 16, which is 25, which is equal to 5 squared. And because one case, and for Pythagorean triples, you can multiply these numbers by any ratio to form any right triangle, because similar triangles, you'd multiply 3 by, I don't know, 3, 4, and 5 by 3, and you'd have 9, 12, and 15. That is also a right triangle. Same goes for 5, 12, 13, 7, 24, 25, yada, yada, yada. So I think whenever you see a right triangle and they're talking about side lengths, the best thing to do is look for a case where you would apply the Pythagorean theorem. Even if they don't give you a right triangle, actually, you can still create a right triangle by dropping what's called an altitude. But actually, I'm going to talk about that later, so don't need to talk about that now. Okay, right triangles, yep. Pythagorean theorem. Okay, so in right triangles, actually the right triangles, you might note that in right triangles, especially, area is really easy. You just have to multiply the two legs together and divide by 2. It's the easiest case where you can prove that base times height over 2 is the area of a triangle. All right, special triangles. So we have some certain cases of special triangles. Let's talk about this. So a 45, 45, 90 triangle has 45 degrees, then 45 degrees, then 90 degrees, because it's a right triangle. What this means is that these two side lengths, the legs, are equal to each other because they are opposite angles that are the same. They are opposite angles that are equal to each other. All right, what's the hypotenuse? We can just find out on our own. X squared plus x squared is equal to c squared. C squared is going to be equal to 2x squared. Let's square root both sides. We get c is equal to x root 2. X root 2. All right, most common place you'd use this is probably when you have a square and they drew a diagonal or something. And you have so what we've proved is that the diagonal of a square is going to be equal to the side length times root 2. Let's talk about 30, 60, 90 triangles. Heck. That's a 60, not a 30. All right, this is different. Why is this? Let's see. If I were to mirror this over that side, note that I would have another 30, 60, 90 triangle, and I would then create an equilateral triangle. So that's important to know. A 30, 60, 90 triangle is created whenever you drop an altitude from an equilateral triangle, from the point of an equilateral triangle. By the way, an altitude is just the line from the perpendicular line from the point of a triangle to the opposite side. Okay, in this case, let's call this x. Because this is an equilateral triangle, we have x, x, and x. But over here, this would be x root x divided by 2 because it's half of that one side. Okay, now we just do Pythagorean theorem again. X half squared plus b squared is equal to x squared. Subtract x squared over 4 from both sides, and we get b squared is equal to 3x squared over 4. Okay, let's square both sides. We get b is equal to, wait, what? I did something wrong. X squared over 4, subtract x squared over 4 from both sides. Oh, no, I didn't. I'm being dumb. B is equal to x root 3 over 2. All right, so this little altitude is going to be x root 3 over 2. All right, but note that x is the hypotenuse in this case. If we were to call this part the side opposite the 30 degrees, the small leg, x, it would be x root 3, and 2x. All right, these are special triangles that are going to pop up. And whenever you see 30, 60, 90, you should immediately be able to come up with these formulas for these equations for the sides of the triangle. Here's a drawing of that. All right, medians. Oh, that goes through the sentence. Like. All right, so medians. Medians are lines from one vertex of a triangle to the opposite end. But what's special about medians is that they go through the exact center of the opposite side. They go through this exact point E. This divides that line into two perfect halves. As you can see, those are congruent. All right. And when you draw all three medians of a triangle, you'll find that they meet at the same point here. We call this the centroid. So if they ask for a centroid, we're talking about medians. It's spelled like this, C-E-N-T roid, R-O-I-D. What's special about the centroid, especially in physics, it's the center of gravity or the center of mass. What that means is if I were to have a triangle and I drew this, and if I knew where the centroid was, I could put my finger on it and it would balance perfectly. But I don't have a triangle to prove that right now. Okay, line from one vertex to the other side. Okay, whenever medians are mentioned, you're pretty much going to have to deal with similar triangles because you're creating separate angles. Area method. What I didn't mention here is always in a triangle with three medians, the centroid splits the medians into a 2-to-1 ratio. So this line is double the length of this line. Same goes for this one here. This is 1, and this one here. Oh, and the smaller part of the median is always going to be closest to the side, not the vertex. Okay, let's move on. Altitudes, yeah, I already talked about those, I guess. When you draw a line from a vertex to an opposite side that forms a right angle, or you could just say you drew a perpendicular line from the side to the opposite vertex. Oh yeah, altitude is what we use, is the height part of the base times height formula. Base times height divided by 2. I guess we already talked about that. Angle bisector. Okay, this is super cool. One of our homework problems went over angle bisectors, but hopefully actually, did I define it? I don't remember if I defined it for you or not, but hopefully you all were able to do a Google search if you didn't. Angle bisectors bisect the angle that they come from. So it's a line drawn from the vertex of a triangle to the opposite side, and it splits the angle of the vertex in half. So in this special case, we can create a theorem called the angle bisector theorem. We have b divided by m is equal to a divided by n. Okay, that looks pretty self-intuitive, right? Here's the angle bisector. We call that CD. And then the opposite sides all form an equal ratio. B divided by m is equal to a divided by n. Okay. You guys can prove this right now, but I'm going to save it for a homework problem. So Not right now. All right, CD squared is equal to A times B minus MN. That's a little funky. CD squared. So that angle bisector is equal to AB minus MN. All right, I'll leave this for you to prove on the homework, but if you still have questions after you see that problem, feel free to email me. But it's important that you memorize the angle bisector theorem. All right, angle bisectors. You'll also find if you like connect all the angle bisectors together. I'm drawing a terrible diagram that I should be doing with the line function. This is the incenter. What that means is I can draw, if I were to inscribe a circle inside of this triangle, the center of that circle would be this circle, this point, the incenter. We haven't talked about circles or inscribing yet, but I guess I can talk. But your circles are just figures, wheels that are all the points that are equidistant from one point. Actually, no, we can talk about that next class. We still have, it's 5:27, and we have still a lot to go through. So let's hurry. Heron's formula. Okay. This is kind of advanced for just the basics, but I think it's really important to know. So Heron's formula is a really cool formula that you can use when you know all three sides of a triangle and you want to find the area. So we call this S the semi-perimeter. So S is going to be A plus B plus C divided by 2. So A plus B plus C is the perimeter, and semi means half. So we're going to multiply the perimeter by 1/2, or cut it in half. And that's the semi-perimeter. And what we know is that the area of the triangle is going to be the square root of the semi-perimeter times the semi-perimeter minus all other sides. So S times S minus A times S minus B times S minus C. Okay. I don't think it might be really useful to know this in some situations, but it's not going to pop up as often as angle bisector or Pythagorean theorem, but it might be good to just know this. That's why I included it. It can be very situational. All right, quadrilaterals. Excuse me, I need to drink some water. Okay. Quadrilateral is any polygon with 4 sides. So we were talked about 3 sides with a triangle, and now we're moving on to 4. All right, 4 sides, vertices, and angles. Let's talk about every quadrilateral in problem solving at this level is going to be convex. So that means that all interior angles are going to be less than 180 degrees. You're going to see obtuse angles, right angles, acute angles, but never reflex angles. All right, what is the sum of all interior angles in any quadrilateral? I think we already talked about this last class, but a good refresher. $360, yeah, Barika says 360, which is absolutely correct. Remember the formula is 180 times n minus 2, in case if you forgot. But let's go on. Squares and rectangles. We already talked about squares and rectangles last class with area. All we have to know is in squares and rectangles, all angles are 90 degrees and both pairs of sides are parallel. I can actually do rectangles. Whoa. Rectangle, square. All right. You see that all 4 angles are 90 degrees and both pairs of sides are parallel to each other. Yada, yada. Squares have the same side lengths. We already know that. In a square, all 4 sides are going to be the same. It's a regular quadrilateral, if you would. All right. This means that, actually, I'm going to ask you a question. Are all squares rectangles?
Yes.
Yes. I'm not going to ask you to explain. Yeah, these 2 points are the only thing that needs to. The first 2 points are the only thing that needs to apply to rectangles. This is only for squares. It's for squares and squares only. In quadrilaterals, if you have the same side lengths, then it has to be a square. That means that not all rectangles are square. That means that all rectangles aren't squares, but all squares are rectangles. Trapezoids. Ooh. Trapezoids are way different. Trapezoids are just quadrilaterals with one pair of parallel sides. Exactly one pair, by the way. You can't have more than one and call it a trapezoid. One pair of parallel sides. Okay, so we call the parallel sides, in this case, AB and CD. Those are bases, and the other 2 sides are legs. EF is an altitude, that would be the perpendicular line between the 2 bases, and X and Y are the midpoints of the legs. So in this case, if X and Y are the midpoints of the legs, then XY is called the median. All right, let's draw diagonal AC and BD. Okay. In this case, XY is going to be equal to AB. Oh, sorry. Oh, yeah. So, the diagonals were just there to define. Okay. So AC and BD are the diagonals. That's where you connect 2 opposite vertices to each other. All right. What's the area of a trapezoid? I already listed it for you below. If we know that the we know that the median is the line between the 2 midpoints of the legs, and we can prove that the median is equal to the average of the 2 bases, or rather, you can just add those 2 bases up and divide them by 2, and the area is going to be the median times the height. Let's draw that. It's going to be something like this, and then connect these together. You'll see that these two leftover pieces can be fit right here to form a perfect rectangle. We're all happy here with our rectangles. Another way you can find it is like you can draw the altitudes from the 2 vertices of a base and then have 2 triangles and a rectangle. That's another way you can do it. I think the next slide is still, yeah, isosceles trapezoids. Isosceles trapezoids is just when the legs are equal or the diagonals are equal or the base angles come in 2 pairs. Let's draw a trapezoid, isosceles trapezoid. All right, so in an isosceles trapezoid, 3 things are true. The legs are equal to each other. That does not look right. I can't get it to look right. Help. Let's go with that. That looks very wrong, and I'm sorry. But let's pretend that these 2 legs are equal. That means that the diagonals are also equal to each other. And the base angles, so that means that these angles are also equal. All right. Here's an area problem for you guys. Find the area of a trapezoid with bases 44 and 24 with height 18. I mean, we already talked about that in the last slide. But hopefully you guys remember. 5 minutes. Wait, 5 minutes. I think we're good. Maxwell says 34 times 18. Cool. So 34 is what the median length is. He found that by adding the 2 bases together and dividing by 2, the average of the 2 bases, if you would. 44 plus 24 is going to be 68 divided by 2, you get 34. Or you can just find whatever numbers between 44 and 24, and that would be 34. And then the height is 18, multiply 34 by 18. I don't want to do math. 34 times 18 is going to be 340 plus close. 240, 508, 5. What? 500 and no. 612, right? 612, nice. Had to confirm quickly on my calculator. All right. Parallelograms. Okay. Parallelograms are defined by having two pairs of parallel sides. So that means squares are parallelograms and rectangles are parallelograms, but not trapezoids. Trapezoids are one pair of parallel sides. All right, in a parallelogram, opposite sides and angles are equal. This is true just by parallels. Parallel lines, the sides are equal and the angles are equal as well. The diagonals bisect each other. So that means that it forces them into two halves. And the area is just going to be base times height again. You would have to drop an altitude and multiply. And you note that this little triangle here can be placed over here to form a rectangle. Cool. Not much to talk about. Rhombi. Oh, I lied earlier. Did I say? I think I said like if all side lengths are equal, then it has to be a square. No, I lied. If all sides and angles are equal, it's a square. But if all sides are equal, you can also have a rhombi, or sorry, a rhombus. Rhombi is plural. Sort of like cactus and cacti. Prove that every rhombus is a parallelogram. Well, we already know that in this case, all sides are equal. We just need to prove that the two sides are parallel to each other. Why is that? Or could we prove that the diagonals bisect each other? That's another way to do it. Tons of ways to do it, but we're running out of time. So let's talk about area. Area, you just multiply the two diagonals by each other and divide by 2. That sort of looks like a rectangle again, but you divide by 2 because you basically formed like 4 mini triangles. The rhombus is formed by 4 mini triangles. All right, cyclic quadrilateral should be last topic of the day. A cyclic quadrilateral is any quadrilateral that's been inscribed inside a circle. Why did I talk about this when we're talking about circles next class? Let's talk about circles really quickly, so we'll have more time next class. All right, a circle is formed of a single point. We call that point the center. And a circle is going to be all the points that are some distance away from that point, some exact distance that we're going to call a radius, or r. So all points on the circle are r away from that point, the center. All right. When we inscribe something inside of a circle, that means that all the vertices of that polygon are points on the circle. So we can have a triangle, or in this case, a quadrilateral. Something like this. All right. The opposite angles of a cyclic quadrilateral are supplementary. So that means that the measure of angle D, in this case, plus the measure of angle B is going to be 180 degrees, and same thing with A and C. That's all you need to know about cyclic quadrilaterals. And so if you are given something that says that a quadrilateral has been inscribed in a circle, though that's only one principle to memorize, the opposite angles are supplementary. All right, I think this is the last slide. No, I still have another slide. All right, problem 6. Okay, this is the AMC 10, but this problem is number 6, so it's pretty much equal in difficulty to AMC 8, number 15 through 20 probably. For how many of the following types of quadrilaterals does there exist a point in the plane of the quadrilateral that is equidistant from all 4 vertices of the quadrilateral? 541, sorry. Does there exist a point? Oh, this is basically asking, when you form the diagonals, when you create the diagonals with each other, when you draw the diagonals of a quadrilateral, do they A, bisect each other, and B, have all four of those little half diagonals equal to each other? Skylar is right. The answer is D. It's going to be the first four, I believe. Right? Am I reading this? A parallelogram that is a rectangle, not a rectangle or not a rhombus. By definition, the sides bisect each other, but no, in a parallelogram, yeah, it's the first three and then the last one. All right, and I will finish today's lesson with just some general quadrilateral concepts. I didn't talk about geometry problems in general last class, but for every geometry problem, you want to draw a clean and neat diagram. You're allowed to have a protractor. You're allowed to have graph paper. You're allowed to have rulers on your exam. And I would definitely bring those to the exam, because when you have really tough geometry problems, you might just want to draw it out. And when you have a neat diagram, you'll see things better and be able to solve things more organized and more neatly. All right, set sides or angles you want to find to a variable. Yeah, we talked about that last class as well. You can turn a geometry problem into an algebra problem really quickly by setting what do you want to find to a variable and finding out what relations that variable has with other things that the problem gave you. All right, rectangles and right triangles are easiest to work with. Yeah, so you want to draw altitudes and diagonals constantly to find right triangles and rectangles, because those are the easiest things to work with, easiest figures. All right, I am done for this class. Are there any questions?
How can there be a point on a rhombus?